So as Stefanos mentioned, I'll be talking about simultaneous wireless information and energy transmission. This is joint work with my advisors, Dr. Samir Perlaza, Professor Vincent Poor, and Dr. Ethan Altman. So let's begin. Here's a brief outline of what the presentation is going to look like. We'll begin by motivating the topic using certain applications and present an overview of what the area looks like and why it's important, why the study of wireless information and energy transmission is important. We'll then move on to explaining how information energy transmission takes place. We'll study the system model in this section and sort of build the problem. We'll then move on to the main results, in which some of the results that we have will be discussed, and in the end, we'll present a few numerical examples, which will hopefully help us solidify what we'll be building up until that point. Okay, so let's begin. So, as we are well aware, in the next generation of wireless communications, which is the 6th generation now, our smartphones will no longer be, will be sharing the landscape with a diverse variety of devices, such as smart wearables, implants, which may be inside the body of a human being, then haptics, and of course a large network of IoT devices, which in itself may consist of a wide variety of devices. Then on the other hand, on the side of applications, in addition to voice and data, 6G will now have to support virtual reality, augmented reality, remote medicine, autonomous driving, to name a few. And then on top of all of this, we have verticals like smart grids and autonomous vehicles. So how does simultaneous information and energy transmission fit into all of this? Let's see. So essentially, this simultaneous information and energy transmission, which we'll be calling SIET for short in this presentation, will act as an enabler for this envisioned ecosystem for 6G. Okay, the primary thing that it is going to provide is a means of remotely powering this large network of low power devices that we are going to have in order to support all of these services. So the low power devices could be sensors and actuators that would have to be deployed all over the place in all kinds of places, which may be hard to reach, to enable all of these services to take place, such as virtual reality and stuff that we looked at in the previous slide. So SIET provides a means to power all of these devices remotely. Okay, hence removing the dependence on manual battery recharging and replacement. So imagine this large network of devices that enables all of these services that you have, but then you have to take care of each of these devices, the battery life of each of these devices. And remember, all of these devices are really small in size, so they cannot support a very large battery size. Okay, so in the absence of such a power source, then SIET provides us a means of maintaining the network without having to manually, take care of these devices one by one. In addition to that, you can think of services like providing access and collecting information from, say, remote or inhospitable environments. And then difficult natural and industrial conditions. For instance, imagine a place where some kind of natural disaster has taken place and which is inaccessible, which is inhospitable for people to travel to. In the absence of, in such environments, SIET could provide us a means of remotely powering sensors for collecting data, for collecting information, or providing certain services where, when you cannot actually go and recharge devices or replace batteries and so on. Then we would also have these devices in hard to reach places, for instance, inside robots, or we talked about implants, so inside the human body. So SIET would encompass all of these things and provide essentially, a sort of energy self-sustainability to the network. So let's understand now what SIET is. So we are all familiar with a typical communication system wherein we have a transmitter or an encoder, a wireless channel, and then an information receiver. Okay. Now, in addition to the information receiver, we also have an energy harvester, which harvests the energy from these RF signals that the transmitter sends. And an important thing to note here is that the energy harvester and the information receiver here may or may not be co-located. Okay, which means that you're not, the energy harvester could also be harvesting energy from signals that are meant for some other information receiver, which is located in some other, some other place in its vicinity. So what are the challenges that this problem presents that, some of which we'll look at today and some of which are still open problems. So the first and foremost thing to note here is that whatever we do here is in the regime of finite block lengths and finite constellation sizes. There is a lot of previous work in this area, which mostly deals with the asymptotic regime. An important difference that arises when we move from the asymptotic to the non-asymptotic regime is that the decoding error probability, which we refer to as the DEP, and the energy outage probability referred to as EOP, can no longer be made arbitrarily close to zero. Okay, so both of these quantities are going to be bounded away from zero. So that is something that we need to account for in all of the and all of the analysis we do, and also in the fundamental limits that we are going to identify. So within this framework, what we want to do is to quantify the fundamental limits of SIET and essentially identify the trade-offs that exist between these two opposing aims of transmitting information and transmitting energy, because we'll see using examples and eventually in our results that often what is good for one for maximizing your information is not the best thing to do for maximizing energy, and vice versa, which is essentially the entire theme of this presentation today. Let's now look at some examples or to provide an intuitive understanding of what we could expect should happen when we arrive at the results, the converse and achievability results that we are going to see. So this is a very high level. So in the next few slides, we're going to have a very high level understanding of what is going on, and hopefully intuitively try to gather what we should expect to happen. And then hopefully when we reach to the point of results, we'll be able to relate it to what is happening here. Okay, so let's begin. So consider this usual QPSK constellation that we're all used to seeing, which has which is 4 points located, 4 points or symbols located in the 4 quadrants. And let's look at this constellation from the perspective of information transmission first, and then we'll do the same exercise for energy transmission. And then hopefully we'll be able to see at that point the trade-offs that I speak of. What is this basic trade-off that I'm talking about, which will hopefully give a good understanding for the rest of the talk. Okay. So in terms of information transmission, the best that we can do with the QPSK constellation is transmit 2 bits, per channel use. So and that information rate is achievable only when all of these symbols are used, uniformly for a uniform trier, because of course, that's a well-known result. And in terms of the decoding error probability, what do the optimal decoding regions look like? We know from the maximum a posteriori receivers that the decoding regions for these for such a constellation would be the 4 quadrants that we see here. So this green region that you see here is essentially represents this entire quadrant between the positive X and Y axes, and that would be the region of correct detection for this specific symbol at the top, the symbol at the top right. Okay. So it's important to note here that there are 4 parameters that mostly that we'll be talking about in this presentation. For information transmission, we have the rate of information transmission and the decoding error probability. And for energy, we have the energy rate of energy transmission and the energy outage probability. So we talked about the DEP and the information rate R for the first constellation. Now let's see what happens in the second constellation that we see now. Now the number of points have increased from 4 to 16. Okay, so and note that the 4 points in the corners are still at the same position as they were in the previous constellation. We have just added more points. Okay, so what happens to the information rate? First of all, we know that the information rate is going to increase because that is a function of the number of symbols you have. The more number of symbols you have, the more messages or code words you'll be able to generate, and therefore higher is the information rate that you'll be able to achieve. Okay, so in going from 4 to 16 symbols, we now go from a maximum rate of 2 bits per channel use to a maximum rate of 4 bits per channel use. Okay. Now, in terms of the in terms of rate, we are doing better. What about the decoding error probability now? So once again, if you look at the decoding, the regions of correct decoding for this particular symbol, it's now smaller, as you can see, than what you had in the previous in your QPSK constellation. Okay. In addition to these, in addition to these kinds of points which we have at the 4 corners, so for all of them, the regions are look something like the green region. Then we have 2 other kinds of points now. So we have points for which the decoding error, for which the region of correct detection looks something like in yellow. Of course, it extends, imagine extending, along the x-axis to the right. And then we also have points for which the region of correct detection looks something like the orange box that you see. Okay. And then once you look at these regions, we can immediately see that the decoding error probability is going to suffer when you go from QPSK to 16 QAM. Okay, so you're gaining in terms of the information rate, but you're losing in terms of the decoding error probability. So you can think of it as sacrificing the decoding error probability to gain on your information rate. Now let's do a similar exercise for energy transmission. Once again, we start with 4 points in the 4 quadrants. And here I use a circle just to represent the fact that all of these points are at the same distance from the origin. Okay, and as we know, the amount of energy that the symbol carries is becomes larger as a distance of as a function of the distance from the origin. So the farther away this point is from the origin, the more energy it carries. Okay. So in this case, E1, say E1 is the energy that these symbols carry, and all of them, carry the same energy, which is all that this circle represents. But our constellation is still the same, 4 points in four of these quadrants. Okay. So in terms of energy, you cannot do any better with this constellation. Okay, there's nothing to think of in terms of energy, because no matter what symbol you use, you'll always be transmitting energy even in a given time slot, in a given channel use. So in terms of energy, there's nothing to optimize, there's nothing to think of. Okay. Then what about the energy outage probability? We'll define the energy outage probability in the system model more formally, but intuitively, what does energy outage probability say? It quantifies how frequently or for what fraction of the time you're going to be in outage. And by outage, we mean, say you have an energy requirement B at the harvester. You want to harvest B units of energy per unit time, for instance. Okay. So your energy outage probability tells you what is the probability that the energy that you harvest is less than this quantity B. Okay, so that is essentially what your EOP or your energy outage probability captures, and we'll have a more formal definition later. So, so what then about the energy outage probability of this constellation? Since you're always transmitting this energy even, no matter what symbol you use, then only one of 2 things can happen. Either this even satisfies the energy requirement at the EH, or it doesn't. If it does, then our energy outage probability is 0. If it doesn't, then it is 1. Okay. So again, in terms of EOP, it's a very simple constellation, and we know we are either always in outage or we are never in outage. Now let's see what happens once again if we add more symbols to this constellation. So I add another set of 4 points to this constellation, which you see in brown now, which have energy E2. Okay, once again, the circle tells you that they are at the same distance from the origin. So these 4 new points also have the same energy, which is E2, which and E2, as we can see, is less than E1. Okay. Now let's look at energy once again. What happens to energy in this case? In some of the time slots or in some of the channel uses, you will be transmitting one of 2 kinds of symbols. So it's either a red symbol that you're transmitting or a brown symbol. If you're transmitting a red symbol, then the energy in that that you're sending in that particular channel uses E1, and or else it is E2 if you're sending the other kind of symbol. So what happens to the average energy that you're harvesting? It becomes, so the average energy that you'll get at the harvester will be somewhere between E1 and E2. Okay, so you suffer in terms of the energy that you harvest. What then about the energy outage probability? So once again, if you're if say the requirement at the EH is to have E1 units of energy per channel use, then in the slots in which you transmit the red symbol, you will not be in outage. But in the slots in which, in the channel uses in which you transmit the brown symbol, you're going to be in outage. And in average, if you look at the average energy outage probability over your entire duration of transmission, it's going to be something other than 0. For instance, if it was 0 in the first constellation, it will not be 0 anymore for the second constellation. Okay. So please note that I use slot, the term slot for channel use sometimes. So the 2 things mean the same thing. If I say a channel use or a slot, it means the same thing. Okay. Okay. So so that's your energy, and that's your energy outage probability. Now, once again, why would you go from the constellation on the left to the constellation on the right? Why would I want to increase the number of points if my energy is suffering? The answer is your information rate, right? The reason I would want 8 points instead of 4, if even though it doesn't benefit me in terms of energy, is because I would require more information. Okay, and then the question would be, why not place all of these 4 points also in this circle of energy E1? Again, the answer lies in your information transmission, because the more symbols you start, accommodating in this circle of energy E1, your decoding error probability is going to start to degrade, because it is a function of the distance between these symbols. So there's a limit to how many of these you can accommodate at a given distance from the origin, and that is constrained by your decoding error probability. Okay, so this is a high-level example of what happens, and to give you an idea of what the trade-offs look like. So the key takeaways that we should expect from this presentation are, first of all, an understanding of the trade-offs that we have in SIET in terms of the information rate, the energy rate, the DEP, and the EOP. Okay, so this would be the key thing to take away from this presentation, which I hope will be made clear by the end of this talk. The other thing that we are going to see is the fundamental limits of SIET, characterized over the simplest AWGN channel. Okay, AWGN channel, as we know, of course, is the simplest model that we can use, but it's also very insightful in terms of the kind of expressions we get. We are able to obtain closed form expressions for several of these parameters, which are very telling, and which are going to tell us, which are going to show us all of these trade-offs that we're talking about. Then the other thing that we're going to do is talk about a method of constructing codes for the purposes of SIET, which would satisfy these different requirements that we have in terms of the 4 parameters: the information, the energy, the DEP, and the EOP. And then the gaps between the converse and achievable regions, information energy regions that we have. What is achieved by this family of codes that we are going to construct, and what is not achieved, what is how close the achievability can get to the converse. Okay. Let's now set up the problem. System model that we're going to use is something like this. So we use a simple point-to-point channel. We have an encoder, encoder at one end that sends, that encodes one of these capital M messages and sends the resulting signal over the AWGN channel. At the other end, the decoder receives, this distorted output Y, which it decodes and tries to figure out what is the message that was sent by the encoder. And on the other hand, we have the energy harvester, which does not care about the information that the signal carries. And we'll see this in the system model as we go along, that the EH does not decode or go through the usual processes that an information receiver would, like down converting and sampling and so on. It just uses the signal that it receives, the RF signal that it receives, for extracting energy. And within this framework, the objective of the system is twofold: to convey information at a certain rate, R bits per second, and convey and harvest energy at some rate of, say, B joules per second over this AWGN channel. Okay, so the channel inputs. Okay, so this is symbolism that we're going to use throughout the talk. I'll try to make this as simple as possible. So we have a set of channel inputs that we denote as bold symbol nu. So everywhere you see bold symbols, they're going to be vectors. And usually capital letters, unless it's avoidable, are going to be random variables. P here is not a random variable. I'll specify where the capital letters are not random variables, but in general, capital letters are used for denoting random variables. And then small letters, of course, are deterministic scalars. Okay, so nu is the channel input vector. Okay, which means that over this duration of n channel uses, each of the symbols that are transmitted are nu1, nu2, so on to nu-n. Okay, so to connect it to the constellations that we just saw, this nu1, nu2 are going to be one of the symbols in our constellation. For instance, in the case of QPSK, nu1 is one of the 4 points. Nu2 is one of those four symbols that we saw in the constellation. And this entire vector is what the transmitter is going to send over the course of n channel uses. F sub W is the baseband frequency that the transmitter uses, and the duration of each channel use in time units is capital T, which is 1 over F. Okay, and using this, the complex baseband signal that is generated at the transmitter is what you see in 1. So essentially, your each of these nu1 to nu-n, along with a pulse, a sync pulse, and m. So this m-1t is essentially the delay, the shift in these pulses, because you're transmitting over n channel uses. Okay. The other thing to note here is that these are complex symbols, but they're essentially, it's important to know that they're just one of those points in your R2 plane, and this is just a matter of representation, whether you want to think of it as nu1 as a complex number, or you want to think of it as a tuple of the in terms of your in phase and quadrature components, depending on which of the two ideas you're more comfortable with. But each of these nus essentially is one of the symbols, one of the red dots that we saw in the constellations. Okay, and then so this is our standard signal processing stuff. The RF signal that is input into the channel is what we see in 2, okay, which is what is obtained after the modulation or upconversion of the signal. And then once the signal is transmitted over the AWGN channel, it undergoes the transformation that we see in 3. So essentially, all that is being done is that a certain noise is being added to the transmitted signal x tilde t. Then what happens on the other end, we have our information receiver, which sort of, as we know, reverses this process that we have been seeing. So it's going to down convert and demodulate our signal, and then sample it to eventually obtain the discrete time complex baseband output, which we see in 4. Okay, so essentially it is your vector, the vector that you transmitted nu plus some noise that was added by the channel. Okay, so each of these is a vector of n elements. So y is a random vector y1 to yn, and n is your random noise. And each of these elements is a complex Gaussian with mean 0 and variance sigma square over 2. And all of these n1 to nn are mutually independent. Okay. Then, as I mentioned, at the energy harvester does not care about the information that is contained in the in ZT. So YT is essentially what the IR sees, and ZT is what your information, your energy harvester receives. And another thing to note is that these N1 and N2 may be the same if your transmitter and your if your receiver and energy harvester are co-located, but they also may be different, depending on the kind of channel that the two devices encounter. Okay. So the EH does not care about down converting or filtering and so on, but uses this received output ZT as is for harvesting the energy contained in it. Now, once again, this is our system model, and within this framework, once again, the two tasks that we want to accomplish are those of information transmission and energy transmission. Okay, now let's look at what the transmitter does for conveying information. Okay, we have a modulation scheme that uses capital L symbols, which essentially means that the number of points that you saw in the constellation earlier is capital L. Okay, so that's what capital L denotes. For instance, for the case of a QPSK constellation, L would be 4. Okay, then we have the set of channel input symbols X1 to XL. And once again, this is each of these would be one of the symbols that is contained in the constellation. The reason we have two different symbolisms here is that so X1 to XL is the number of symbols that are available to you because of the constellation that you're using. And this new 1 to new M represent the symbol transmitted in channel use. And as we'll see, we need both of these things because we need a way of representing what is transmitted in channel use N. And of course, set XL is set X is something that is defined by the constellation. So the number of messages that can be generated using these L symbols is capital M, which is less than or equal to 2 to the power n log of L. Okay. Once again, this is an upper bound. This is the maximum number of messages that we can generate, and this so this holds with equality only when we have a uniform prior. That is, we are using all of the symbols uniformly. Okay. And then the information rate that is obtained or that is achieved is log of M over N, where N is the number of channel users that we are considering. And the objective of the information transmission is to convey information at a certain rate R, while respecting a certain decoding error probability. Now, what is the decoding error probability? We'll see in a bit. So, in order to achieve this goal of information transmission, the transmitter uses an NM code, which we now define. So an NM code is essentially this set of code words, okay, U1 to UM, along with the regions D1 to DM, which are the regions of correct detection for each of these code words. So for instance, U1 would be the code word corresponding to the first message. You have M of these messages, and corresponding to every message, you have a code word, which means that in order to convey message I would transmit the code word U of I. Okay, and the corresponding region of correct detection is D of I, which is what the receiver is going to use for determining that the code word I was transmitted. So for instance, if U1 is one of the QPSK symbols that we saw earlier, let me just quickly go back to that figure. So say actually, yeah, sorry. So this is the decoding region in terms of the symbol, but DI that we talk about in the other slide is the decoding region for a code word, and we'll see how the two relate to each other. But say for instance your N is just one, you're just using one channel use. In that case, the code word would just be one symbol. And in that case, essentially, if this is U1, this is exactly what D1 would look like. Okay, and then the requirements that we have that we have to impose are, of course, that the decoding regions have to be mutually disjoint. So this is what we need for proper detection at the information receiver, because if the two regions overlap, then there would of course be a region where you don't know whether U1 has been transmitted or U2 has been transmitted. So you need, so we need these regions to be mutually disjoint, and the union is some subset of Cn. And we also impose a peak power constraint that you see in 9, that each of these symbols UMI cannot have magnitude any more than P. Okay. Once again, here UI is the code word which is composed of N symbols. So U1I, U2I, so on till UNI would also be, one of those L symbols that we have. Okay. Now, within this, using this code C, so we use calligraphic C to denote a code of an NM code of this form. Okay, in order to convey message I, the transmitter would use the corresponding code word U of I. So which means that the symbol U1I would be sent in the first channel use, the symbol U2I would be sent in the second channel use, and so on and so forth until the channel use N. Okay. And then at the other end on the side of the information receiver, once this vector Y is received, the receiver decides that the code word UI was transmitted if Y belongs to the region DI, which is essentially the definition of our region of correct detection. And using this, we can now define the average decoding error probability for code C, which is what you see in 13. So essentially what 13 states is, what 13 calculates is your probability. So this integral that you see here is the probability of correct detection for the code word UI, and 1 minus that quantity gives you the probability of error. And then of course you average over all of the M messages that we have. Okay, and using this, we can now define, we can refine the definition of the NM codes that we saw. So in addition to everything that we saw in the definition of an NM code, if the code C also obeys equation 14, which states that your decoding error probability is always less than some quantity epsilon, then such a code is referred to as NM epsilon code. Okay. So NM, so we had a basic NM code, and now we have added to it a layer of complexity in some sense, which forces it to also obey a decoding error probability of epsilon. Okay. So with all of this, we can now define what we call as the type. Okay. The type essentially, so this is something that the reason we define we use this definition at this point is because as we'll see in the results finally, the thing that connects all of these parameters that we have is the type. Okay, what is, so let's define it. We have the type induced by a code word, which essentially tells you the frequency with which a symbol appears in a code word UI. Okay, that's essentially what 15 calculates. So what is P UI of X? So given some X in the set of your symbols, PUI of X tells you how frequently, with what frequency does X appear in U of I. That's all that it does. Okay. Then the type induced by a code C is denoted by P sub C, and this is essentially how frequently does X appear in the entire code C. Okay. So that's all that PUI and PCX are telling us. Okay. And using this, we can define a specific class of codes which are going to be of interest to us, which is homogeneous codes. So homogeneous codes are essentially codes for which these two types that we see, PUI is equal to PCX. All that means is that, for instance, if a symbol X we say appears with frequency P in the code, then in each of these code words also it appears with frequency P. What does that mean? For instance, if we say that in the entire code, every 2 out of every 10 symbols is X, okay, then the same type will be respected in the code in every code word as well. So in each of the code words also, 2 out of every 10 symbols is X. Okay, so that's essentially what this definition means. And we'll see that this is it's useful to think of homogeneous codes in several results, as we'll see later, because it allows us to it often allows us to see to obtain essential insights from codes, and in some cases simplify the expressions which are sort of more insightful and more telling. Okay, so that was all for the information transmission part. Now for the energy transmission, the expected average energy that we are able to harvest from a message I is given by 18, okay, which is a function of the magnitude squared and the magnitude to the power 4 of the symbols that are contained in a message I, which can be one of M messages. So this is this expression is obtained from the reference you see here. This is one of the references. This is just one of the series of works that arrive at this expression. So the important thing to note here is that we see a power UIM to the power 4 in addition to the squared terms which we are used to seeing in energy. And the reason is that the reason for this term is the nonlinearities that the energy harvester that are introduced by the energy harvester circuits due to the presence of nonlinear elements such as diodes and capacitors, and they arrive at the expression in 18. So essentially, EI is the amount of energy that I'll be able to harvest if message I is sent. So at the end of n channel uses, EI is the energy that obtained. And note that this is not a random variable. I know the symbols that are contained in my in this code word I. So EI is something that is a definite quantity. We know that if I transmit UI, I'm going to harvest energy EI at the end of n channel uses. Okay, and once again, the objective of this energy transmission task is to ensure a certain energy B is harvested at the EH at the end of these n channel uses. Okay. So within this framework, we can now formally define the energy outage probability. Okay. So denote by this capital W, for instance, the message that is transmitted in the message that is being transmitted. So the probability of transmitting, assuming a uniform prior, that all of the messages are transmitted uniformly. Okay, one of these M messages is transmitted with probability 1 over M. So this is essentially the frequency with which I'm using these. I'm sending one of these M messages. So note that the energy that you're going to harvest at the end of n channel uses is a random variable E. Okay, so indeed the energy that you harvest given a certain message is what we see in 18, which is not a random quantity. However, because of 19, because we don't know which of these M messages is going to be transmitted, the energy that you harvest at the end of n channel uses is a random variable. Okay, And the conditional probability of harvesting harvesting energy E, given that I was transmitted, is what we see in 20. So essentially, with probability 1, we harvest EI, and that's all we have, because now using because of equation 18, the energy that you're harvesting is discretized. So it's only one of these M levels is possible. Therefore, the conditional probability looks like 20. Okay. And then using this, the probability that energy E is harvested in N channel uses is denoted, is given by 21. So using this, we can now define the average energy outage probability, which we denote by theta CB, as what we see in 22. Okay, so it's essentially the probability measure of this interval 0 to B, because we are interested in having energy equal to or greater than B. So anything less than that means that the energy harvested is an outage. Okay, which sorry. Which is equal to this quantity that we see in 25. Let's understand this a little more clearly from a small dummy example. So note here that in 25, what you have is the sum of indicators indicating whether EI is less than B or not. Okay. So what it essentially means is that given for instance, say we have these 7 symbols, 7 messages, you want to use 7. So E1 is the energy of U1, E2 is the energy of U2, so on and so forth. What does this the expression in 25 tell us? The expression in 25 tells us that I want to find out how many of these fall below this requirement of B, and then I sum them up and I divide them and I divide that quantity by M, which is what gives me my energy outage probability. So for instance, all of the red symbols all of the red code words have energy less than B, and all of the green ones have energy more than B. Therefore, my energy outage probability in this case is going to be simply 3 out of 7. So essentially your energy outage probability now becomes a discretized quantity. It can only take values from either 0, 1 over M, 2 over M, so on till 1. And for the case of homogeneous codes, it can only be 0 or 1. Okay, once again, recall that my homogeneous codes are the kind of codes in which every symbol appears, with the same frequency in all of the code words. Okay. Therefore, from 18, you can see that for the class of homogeneous codes, this EI is going to be the same for all of my code words. Why? Because this, it's essentially a function of the magnitude of my symbols. So if the symbols appear with the same frequency in all of the codes, the energy that you harvest from each of these code words is going to be the same. So essentially for a homogeneous codes, this theta CB can only be 0 or 1. So either we are always in outage or we are never in outage, because all of these bars that you see here are at the same level. So either all of them are more than B or all of them are less than B. Okay, so using this idea of energy outage probability, we can now add, another layer of a refinement to the codes that we have been defining. We saw what NM epsilon codes are. Now, in addition to everything that we see until that point, if on top of that the code also respects 26, okay, which says that my energy outage probability is less than delta, then such a code is referred to as an NM epsilon B delta code. Okay, so we now come to the main results. I would like to pause here, and I know that Stefano said that we can take questions only in the end, but if there's a pressing question that will not let you understand the rest of the talk, please feel free to ask right now. Is that okay, Stefanos? Okay. So I assume that means that there are no questions. So let's move on to the main results. So in this section, I would like to focus a little more on the code construction, because again, this provides a lot of insights as to what is what the different trade-offs are, and how all these factors interplay. And then, of course, we'll move on to the expressions for the bounds on different quantities. And okay, so we provide a construction of codes for SIET, okay, in the form of layers. So layer is essentially a subset of symbols in the complex plane that have the same magnitude. So each of these the black circles that you see here is what is called a layer. And we construct a constellation in terms of these layers. Okay, so say for instance, this particular constellation that you see has two layers. The outer layer has the red symbols belong to the outer layer, and the brown symbols belong to the inner layer. And as we have seen before, the outer layer has more, the symbols in the outer layer contain more energy than those in the inner layer. We denote by capital A sub 1 the radius of the outer layer. So similarly, A sub 2 is the radius of this inner layer. And the small r's, okay, we'll talk about the small r's in a bit. So within this framework, a layer is essentially a collection of symbols that have the same magnitude, and we denote such a layer as U sub C that you see in 27. So a layer is denoted by the letter small c, and XCL denotes a symbol in the L symbol in the in layer C. Okay. And my constellation X is essentially the union of all of these, the symbols contained in all of these layers. Okay, so that gives me the position of my symbols and the number of symbols that I have. The other thing that we need to define a code is the decoding, is the region of correct detection. Okay, in this construction, we make use of circles centered at the symbol to define a decoding, to define the region of correct detection. So each of these circles, dotted circles, dashed circles that you see represent regions of correct detection of these symbols. Note that this is a suboptimal choice. We know, for instance, from our understanding of the map rule, that the optimal decoding regions would not look like this. They would look, they would say, for instance, be something of the form of cones for the symbols in the outer layer. But we are restricting ourselves to a circle, which is a suboptimal choice. However, this is a construction, so this is the construction choice that we make, and we'll see that it has an impact on the decoding error probability, of course. But for the purposes of this for the purposes of this construction, this is a choice that we make, and we'll understand in a bit why we do that. Okay? And each of these are the small r's define the radius of these decoding regions. Okay, so essentially, for the first layer, R1 is the radius of these decoding regions. For layer 2, it's R2, and these the R1 and R2, of course, don't have to be the same; they could be different. So. Okay, then the other thing that we need for defining the entire code is the frequency with which each of these symbols appear in the code. We use P sub C to define the frequency with which symbols from layer C appear in the code. Again, the thing to note here is that PC, is not uniform. We don't use all of the layers with the same frequency. And why is that? So for instance, what would be the need for making PC anything other than uniform? Why would I use one layer with a greater frequency than the other? The answer lies in your energy requirement. Okay, so for instance, the best that I can do with this constellation in terms of information I know is to use all of the symbols with the same frequency. But if I do that, okay, there'll be I'll be using one of these 4 brown symbols also with the same frequency as any of the red symbols. Okay, but if the energy that I obtain using that does not suffice my energy requirements, then what I would like to do is use the outer layer with more frequency than the inner layer, which is why, the PC is important, because it defines which of the symbols from which layer I use with what frequency. Okay. So the point I want to convey is that the whole point, the only reason I would use one of the layers more frequently than the other is for the sake of energy. Okay. Then within a layer, all of the symbols are used with the same frequency. So if PC is essentially the frequency corresponding to layer C, but then each of the LC symbols in that layer are used with the same frequency. Again, the point being that all of these, the whole point of using anything other than a uniform distribution is to obtain more energy. But all of the symbols in a particular layer carry the same energy. So it's not in my interest to use any of, say, any of the red symbols more frequently than another red symbol, okay? Because I'll not be gaining anything in terms of energy, but I'll be losing something in terms of the information rate. Because again, remember that the farther you go from a uniform distribution, the worse your information rate is going to be. So essentially, PC by LC is the frequency with which I use a symbol from layer C. And then 32 essentially tells you that the decoding region that we saw in terms of circles. So RC is the radius of the decoding region for symbols in layer C. These are some of the notations that we have. The vector of these radii of decoding regions we represent by bold R. The vector of amplitudes is denoted by bold A sub C. And again, note that if you recall the definition of an NM code, we require the regions of detection of these symbols to be mutually disjoint. Okay, to ensure that, essentially, what we want is that none of these circles should be overlapping with each other. They have to be mutually disjoint. So what you see in 33 is the most trivial case. For alpha C equal to 0, which is essentially, so alpha C is essentially the phase shift, the relative phase shift of each of these layers. So say, for instance, if you look at this layer, my first symbol, appears in line with the x-axis, but the first symbol in the second layer is, shifted by a certain angle alpha. Okay. But in the worst case scenario would be when the two symbols align completely. So what would happen in that case is that the two decoding regions are also, the two circles are in line with each other. So in the worst case scenario, what I need is for the difference between the two radii of two layers to be at least equal to the radii of their decoding region. So essentially, this distance between the two layers has to be at least R1 plus R2 for the worst case scenario. Of course, we can do better if alpha C's are, if these relative phase shifts between the symbols in the two layers are carefully curated. So again, LC alpha C are vectors that we use for denoting this family of codes. And with all of these definitions, we are able to define a family of NM codes, which we denote by 39, where C is the number of layers in this code, in this family of codes. AC is the vector of amplitudes. LC is the vector of the number of symbols in each layer. P is the vector of the types, and R is the vector of the radii of decoding regions. And together with all of these, this family of codes is completely defined. Okay, so now we arrive at some of the main results of this work, which is essentially quantifying the bounds on all of these parameters, on your rate, information rate, your energy rate, your DEB, and your EOB. So the first lemma states that given any NM epsilon B delta code C in this family, of the form that we just saw, the decoding error probability satisfies the inequality that you see. Okay. So again, note that here, all of these results are put in terms of the kind of codes that we constructed, but the results are actually more general. We also have expressions for, of course, the most general form of an NM epsilon B delta codes. But here, since we are talking about a specific kind of codes, we'll talk about these results also in terms of, the kind of codes that we constructed. So given any nm epsilon delta code of this form, epsilon, the bound on epsilon looks like what we see what we see in this lemma. So essentially, the important thing to the interesting insight to derive from here, and we'll also see this. We will also be able to see this in the numerical results more clearly. That this is a function of the minimum distance between the points, which we know from the union bound on the decoding error probability as well. So as the minimum distance between the points decreases, the points in your constellation decreases, so accordingly your epsilon increases. So the farther apart your points are going to be, the lesser your the epsilon that you'll be able to achieve will be lesser. Okay, which is essentially what we also intuitively discussed in the examples at the beginning. Then the second lemma gives us a similar bound on the information rate R of C. So given any nm epsilon B delta code, the best you can do in terms of information rate is what you see in 40. Then similarly, a bound on delta. Once again, the energy outage probability delta satisfies what you see in 41. So essentially, you cannot, so anything out. So essentially, what the converse region quantifies is that anything outside of this region is not achievable. It tells us that it essentially gives us or characterizes the tuples of R, B, epsilon, and delta, which cannot be achieved by any code. Then the achievability bounds tell us, the other side of the story. It tells us what can be achieved by, using the kind of codes that we constructed. And the first, so once again, we have a bound on the DEP first. So the lemma tells us that given any NM code in the family that we constructed, the code is an NM epsilon code if 42 is obeyed, which means that the RCs that you have, for instance, the parameter that appears here is RC, and then your type PUIXCL. So essentially, if these parameters obey equation 42, then the NM code can be guaranteed to be an NM epsilon code as well. Similarly, a bound on RC. So essentially, this tells us that if you have an NM code, then the best you can do in terms of the information rate R is what you see in 43. And plus, here, note that we have the term LC here, which is also a parameter of the code. And LC can be at most pi by 2 arc sine RC over 2 AC. Where RC, remember, is the radius of your decoding region in layer C. So LC is essentially, if you think in terms of the constellation, LC is the number of these balls that you can accommodate, for instance, on in each of these layers. So the greater is, for instance, the stricter is your DEP requirement. For a stricter DEP requirement, you would want these circles to be larger, the dashed circles to be larger, which means that the number of these that you can accommodate in a layer is going to be lesser, which is exactly what this tells you. So the greater is my DEP, so this RC that I'll be able to have is a function of this epsilon that you see in the first lemma. And then using this, so the DEP fixes the RC fixes the LC, and then the LC in turn fixes the best you can do in terms of R. So once again, the trade-offs are made very clear by the kind of expressions that you get, and they intuitively hold true with what we know from an intuitive understanding of this. Okay? And then similarly, a bound on delta, which tells us what is the best, what can be achieved in terms of the energy outage probability. What is the B that sort of can guarantee a certain delta? Okay. So we end with a couple of numerical results. So for these numerical results, we make use of a 2-layered code, which means that we have 2 of those collection of symbols that we saw, and there are 5 symbols in each of those 2 layers. The outer layer is at a distance of 20 units from the origin, and the inner layer of radius A2 is varied, as we'll see in the 2 plots. and the frequency with which the symbols from the layer A1 are used is P, and correspondingly the frequency with which the symbols in layer 2 are used is 1 minus P. And in this case, we consider a homogeneous NM epsilon B delta code, which means that the energy that we can harvest from all of the code words is the same, which is denoted by E. So essentially, no matter what code word you transmit, the energy that you'll be harvesting is the small e. Okay. So the first thing, so here we see the variation of information rate as a function of the harvested energy. And this is something very interesting to note. So what we note is that, so each of these curves is, first of all, for a different A. Okay, so something obvious that you can immediately see is that as this A2 increases, the curves shift to the right, which means the energy that you can harvest increases. And why is that? Because, as the radius of the inner circle increases, so the overall energy that is carried by the code word is going to increase. Therefore, of course, the energy that you harvest is going to increase. Then within each of these curves, we see that as a function of E, the information rate first increases and then decreases. And why is that? Because for each of these points, the P is as indicated. So again, recall that P is the frequency with which you are using the symbols from the output layer, which is the layer that has a higher energy. Okay, so so as this P increases, okay, your energy rate is of course going to keep increasing because you're using the symbols with higher energy with more and more frequency. So as P increases, your energy is definitely going to increase, okay, which is made clear by this figure. But in terms of the information rate, the information rate first increases until you get to the point of P equal to 0.5, which corresponds to uniform type, because again, recall that we have the same number of symbols in both the layers. If we had say greater number of symbols in one of the layers, then this peak would be obtained at a different P, okay, which would correspond to using all of the symbols uniformly. In this case, it is 0.5 itself. So until that point, the information rate is going to increase. But beyond that, once again, you are deviating from uniform type. So your information rate is once again going to decline. Then the decoding error probability as a function of once again the probability of using the outer layer, and we see that as this A2 increases, the decoding error probability increases. And once again, why is that? That is again something that's very telling, because as A2 increases, the distance between your points in the constellation is going to decrease. So essentially, the inner circle is increasing, and your points are getting squished together more and more, which means that the distance between them is decreasing, and which leads to a higher decoding error probability at the cost of energy, of course, because as we saw, as A increases, the energy increases, but then the decoding error probability is going to suffer. And that's it from my end. So all of these materials are available in on archive and Hall, and you can find them on my webpage. And of course, I'm open to any queries that you may have. And let's take some questions now if you have time.